Alright, so let's say there's a limit here, and the question wants you to compute the limit of the above function. To start, this is a limit at infinity, as we can see by the expression here. What is a limit at infinity? A limit at infinity looks at what happens to a function as x becomes very large. So instead of asking what is the value at some point, essentially what we're asking is what does the function approach as x keeps increasing forever? So what's the basic idea? We write limits at infinity in this form here, where the question mark will tell us the end behavior of the function. How does this work in practice? So we can apply this to our example. This is our example here. How do we find this solution? Step one is to look at what the highest power of x is. Since we're taking the limit with respect to x, the highest power of x will become the largest the fastest. So for example, when we apply very large x values to x to the power 3 and x to the power 2, we'll see that the x to the power 3 value is much larger. So this x to the power 3 value is more important. This is very key for computing the limit at infinity. In our example, we can see that x to the power 2 is going to be our largest power, seen in both the denominator and the numerator. The next step, once the highest power is identified, we multiply the numerator and denominator by 1 over this highest power. We identify that x squared is the highest power, so we can multiply both the numerator and denominator by this 1 over x squared, distributing it to each term. And if we do that, we get this expression here. The next step is to apply the limit, but first we can cancel out the x squared terms because they appear both in the numerator and denominator for this term on the top and the term on the bottom. And then we can also cancel out one of the x's in the x over x squared term, which if we do that, it leaves us with this expression here. So looking at these three terms here, what happens when x gets very large? Looking at 5 over x squared, for example, let's plug in 5 divided by 1,000. We can see that it's a small number, 0.005. As we increase x larger and larger, this number will get smaller. So for very large x, we can say that it approximately approaches 0. And this same behavior can be seen for 1 over x. As x becomes very large, this expression goes to 0. And that same behavior also is seen in the 1 over x squared situation. This means these three terms are going to go to 0 in the infinity limit situation. This will just leave us with 3 over 2. This is the final answer. This means that the function gets closer and closer to 3 over 2 as x grows larger. So the key rules to remember when computing infinite limits is the highest power is the same. The limit is the ratio of the leading coefficients. As we can see in our example here, the highest powers were the same in the numerator and denominator. You can see that we were left with just the leading coefficients of the top and the bottom terms. In another situation where the top degree is smaller, the limit is 0, because if we take the limit in this situation here, we can see that the top degree is smaller. We can cancel out one of the x's, leaving us with this, and we already seen that the limit as x goes to infinity of 1 over x is 0, so we get 0 in this case. And the last situation you can see is if the top degree is larger, the limit is positive infinity, because we see that the top degree is larger in this situation here. If we cancel out one of the x's, as x goes to infinity, our function x is going to also just go to infinity. So these are the three possibilities when taking an infinite limit.